All right, I can start?
Yep, Bettina, go ahead.
Excellent. Well, first of all, thanks a lot for having me in the COMSOC seminar series. And I would like to present a joint paper with Claudia Mayo. And I sometimes like to also tell a bit how paper came about. And last year I visited Claudia in Naples. And we started talking about another project of hers, which has to do with housing markets with externalities. And while we were looking at that, I was thinking, well, you know, maybe these are very strong externalities you're looking at. That's of course something one can do, but maybe there is some more milder form of externality that would allow for more positive results. And so we started thinking a little bit, and that's when we came up with this topic, and we started working on that. And now yes, it's moving. So our point of departure is the classical housing market by Shapley and Scarf. So just in order to set the stage, that means we have n agents and we have n indivisible and heterogeneous items. Now in the original paper, they say, well, each agent owns a house. So these indivisible items there were called houses, and that's why we call those housing markets. And each agent owns one house, and they want to have one house, and we don't have monetary transfers. So the only thing agents can do is swap the houses among themselves, and hence we have a very simple exchange economy here. Now, in this case, the only thing the agents care about is the house they receive or the object they have. Now, what is new in our approach is that we look at externalities, but they are limited. And of course, I should explain to you what that means. So just more generally, of course, externalities, most generally, externalities always cause trouble, right? And in this specific context, we are not the first people to look at externalities for housing markets. Now there's a paper by Mungchun Saklam, where they show that if you have any externality, so any possible externality, so in fact, agents have just preferences over the whole allocation of houses to all the agents, the core may be empty. Now, then there's another paper that we have found by Hong and Park, where they look at so-called egocentric preferences, where essentially the agents care most about the houses. I'm going to say something about that preference domain later on. And then as mentioned to you, I talked to Claudia about their paper, which looks at, so this Hong and Park paper, they look at the existence of core solutions and the top trading cycles rule for this egocentric preference domain. Now, Claudia's paper with their co-authors, Graciano and Yanelis, they look at existence and uniqueness of stable sets for two specific preference domains. Now, they allow quite some externalities. They are structured, and I'm not going into details here because our paper is about a different type of externality. So we started working on our paper, getting results. And then later I go to Australia and I meet Haris, and I'm presenting this paper, or the first results we had, in a little seminar in Sydney. And then Haris said, oh, you know what? We actually have a paper about this. It's exactly the same model. Now, the reason why this was escaping our attention at that moment or before was that they call it the temporary exchange problem. So we were talking about housing markets with externalities, and they were talking about the temporary exchange problem. So the Google search that we did didn't show this, but luckily we talked about it. And in fact, you know, there are relations. And of course, when you see that somebody has a paper on the same topic you have, you get a shock. But luckily there are complementarities in our results and their results. So they're looking a lot at computational complexity of, you know, finding out whether there is a co-allocation or not, whether there's a Pareto efficient allocation or not. And they also have some partial axiomatic results that are relevant for our setup. So I'm going to mention that later on. So this is basically the literature we found on externalities for these housing markets. And maybe now let me tell you about what we actually do. So of course, the premise is that there is an externality. Each agent does not only care about the house he or she receives. So, and the limitation in the externality is that the only other thing you care about is who receives your house. So we don't care so much what other consumptions the other agents have, We just care about who gets our house. Now, a good example of this setup is actually a house example where we talk about the vacation house. So suppose each of us has a vacation house and we have been going there for vacations for many, many years. So it turned a little bit boring, and also suppose that we can freely travel. So then it's natural to say, well, listen, maybe we should swap our vacation homes. Then we get to have a vacation somewhere else, and everybody's happy. Now, in that example, it's clear that you care about where you go on where you have your vacation, so which vacation house you get, but you might also care about who is in your house, right? It's your vacation house. So maybe you prefer a family over a group of teenagers who will party all day long and who don't clean up very well. Now, the other example you could think about is that of teachers or professors and teaching bundles. So maybe you're allowed to swap your teaching assignment with somebody else, and then of course you care about what you teach, but you might also care about who's teaching your courses because you care about the students. So that would be another type of example that we can think about. So by the way, while I'm presenting, I don't see the chat. So I asked Dominik to at some point read questions if they are happening to me. I can't multitask very well. I can't present and look at the chat, so I'm sorry for that. Okay, so here's the model. We have a finite set of agents and a finite set of houses, and it's the same number of agents and houses. Now, an allocation is an assignment of the houses to the agents. And the specific starting allocation is the endowment allocation, where we assume that agent 1 owns house 1, agent 2 owns house 2, and so on and so forth. Okay. Now, an allocation induces allotments to the agents, and the allotments is what these agents consume. And in this case, the consumption isn't only the house you get, but also who gets your house. So I hope you can see the mouse. So basically, your allotment is the house you consume and who is going to consume your house. And in the end, that's what you are having preferences over. So one specific, AI are the allotments of agent I. So a very important restriction is that for the endowment allocation, if you have your house, you also are consuming your house. So that makes this model just slightly different than a higher dimensional so-called multi-type housing market. So there is this connection between these endowments, and that changes things slightly around. So this model is not equivalent to a multi-type housing markets where you own houses and cars and you get to swap each of these objects among each other. Okay. Now, given that we have these two items for our allotments, we started focusing on a specific type of preferences that seem very natural. And one natural thing would be that we assume that you have preferences over the houses. So you care about which courses you are going to teach. And we call these selfish preferences. So you have a selfish strict preference relation over the houses. And at the same time, you also have a ranking of the agents, for instance, who are going to teach your courses. And in this teaching context, we thought, since you care for the students, you care about who's teaching the course, we came up with the name of altruistic strict preferences. As I mentioned, preferences are strict. So we have these two linear orders over houses and agents. And then it's natural to look at the preference domain where preferences are responsive to these linear orders. And hence we are looking at separable preferences. Now, as you can see, there are some formulas on the slides. I'm not going into details here, just explain informally what we mean. So we are assuming that preferences are strict over the allotments. Now, in the original model, that's not the case. If I only care about which house I'm consuming, I'm completely indifferent between any allotment that gives me a specific house and Dominik gets to stay in my vacation house versus I get the same house and somebody else stays in that vacation house. In the original model, you're indifferent between all of these allotments. But in our case, we assume you have strict preferences over who stays in your house as well. So then what we ask is that preferences are separable, or as I said, responsive to these linear orders. There are different names used for the same thing sometimes. So what does it mean? It just means that suppose I have an allotment and I just replace the house by a better house, I get a better allotment. And if I have an allotment and I replace the agent by a better agent, I also have a better allotment. On top of that, since we are going to think about individual rationality later on, we know you have an endowment. So when both the house and the agent are better than your endowment house and yourself, then we say that this has to be a preferred allocation to your endowment. And if the house is worse than the house you have and the agent is worse, then you have a worse assignment. So those are the formulas. So this means separability of preferences. So here's just how this looks like when we have 3 agents and 3 houses. Clearly we have 6 allocations, and these allocations are allocated, induce allotments for the agent. So here agent 1 gets house 1. Well, this is just the endowment allocation, so this is a bit boring. A2, agent 3, agent 1 receives house 3, and who gets his house? Well, agent 2, right? Here you see that agent 2 gets agent 1's house, so his allotment is H3 2. So this allocation induces the allotments to the agents. Okay, and if we think about those separable preferences, it could be that agent 1 likes house 2 over his own house over house 3, and he prefers agent 3 over agent 2 over himself. Okay, so this is an example. This just means that these agents are acceptable to him. And here we just list an example of separable preferences. So you can just check that if you have house 2, you like agent 3 better than agent 2. And the same happens when you have house 3, 3 is better than 2. And you can check that for all agents and for all houses. So this is going to be separable. The second preference relation for agent 1 is not separable. So here you see that when you have house 2, you prefer agent 3 over agent 2. But when you have house 2, you prefer agent 2 about agent 3. So you flip the preference over those 2 agents, hence it's not separable. Okay. So we are interested in core allocations, and hence we do define what the core is, and it's the standard. These are standard definitions, just using our specific preferences. So we first look at the blocking notion that is going to induce the core. So we say that the coalition S can strongly block an allocation A if there exists another allocation B, such that the agents in S reshuffle the houses they own among themselves. This is condition A. And such that all of them, by doing so, are strictly better off. That's condition B. So, and the strict blocking, if there is strict blocking, then we say that this allocation is not going to be in the weak core. So an allocation is a weak core allocation if there are no strong blocking coalitions. So this is very typical. Now you can observe that this blocking notion is defined with strict preference. Alternatively, we could just change this condition here into this condition over here, where we require the coalition S to reshuffle the objects such that all of them are weakly better off and at least one of them is strictly better off. So that means some of them could be indifferent. You just have the same house and the same agent stays at your place. Now this is a weak blocking, and if we don't have weak blocking coalitions, then we are going to talk about the strong core. Now by the definition, we immediately see that the strong core is a subset of the weak core. So this is very typical. So what are we going to do? We look at the existence of weak and strong core allocations, and the factors that play a role are the number of agents, and also a little bit the acceptability or unacceptability of agents and houses, and the preference domains. Now, there are 2 relevant benchmarks. Without externalities, the strict core allocation always exists. And we know that it can be found with the top trading cycles algorithm. It's in singleton when preferences are strict. And when we have arbitrary externalities, anything goes and the core is frequently empty. Okay, so those are the benchmarks. And we try to be a little bit in between and categorize what's going on. So if we look at separable preferences, for 3 agents, if there are only 3 agents, then the strong core is equal to the weak core. By the way, I have the tendency to say strict core and strong core. I actually mean the same thing because those both terms are used in the literature. So if we have 3 agents, strong and weak core are coinciding for separable preferences. And when there are 3 agents and we have only acceptable agents and houses, so your house is the worst and you are the worst person, so to speak, then in fact this is a non-empty set. And it could be multiple, there could be multiple such allocations. Okay, so how do you prove this? Now this result we prove by exhaustion. There are 4 possible types for each agent. And then we have 64 cases, and then we can regroup them, and each of these groups we can construct a core allocation. And we have multiple core examples. Now, if we have more agents and only acceptable agents and houses, then it is possible that the strict core is empty. Now, if we have only 3 agents and unacceptable agents and houses, then the core can be empty. So we have some possibilities that the strong core, the strict core is empty, which of course also means, it doesn't mean that the weak core is empty, but this one might be empty. So the next question we ask is, can the separable preference domain be restricted further to guarantee coexistence? Okay. And one natural domain is sort of going back to the previous situation where you, for instance, care mostly about your vacation house. So where are you going on vacation? And we now talk about lexicographic preferences. And of course, you have 2 types of lexicographic preferences. Either the houses are important to you primarily, and then secondarily, the agents who stay at your house, or the other way around. So this gives 2 different preference domains, the selfish lexicographic preference domain, and then the altruistic lexicographic preference domain. So I look at, for the selfish lexicographic preference, you look at 2 allotments and you first check, do I prefer this house over that house? If you already prefer house H over house H prime, then the allotment is already better. Now, if it's the same house, then the agent staying in your house is tie breaking. And when the better agent stays in your house, you prefer that allotment. And you similarly do the same thing for altruistic lexicographic preferences. Okay. Now, obviously, the selfish lexicographic and the altruistic lexicographic preference domains are disjoint. Now, here's just an example of a selfish lexicographic preference. You see that house 3 is the best, then house 2, and then house 1. And then the agents are separable. Here it's the other way around. You see that agent 3 in your house is your preferred, is a preferred option, and then 2, and then 1. And of course, you can have separable preferences that are neither selfish lexicographic nor altruistic lexicographic. So here, for instance, you see that you know, H3 comes before H1 and then H3. So you know, you cannot be selfish lexicographic because you know your preference changes between houses, and then you can see something similar for the agents. Okay. So if we now have several preference domains. So one of the things we just quickly do is we draw a little Venn diagram showing you that the general domain of strict preferences is the largest preference domain. Then we have separable preferences. Then we have so-called additive separable preferences. I didn't introduce it to them. I think many of you know what that is. And then we have the selfish and the altruistic lexicographic preferences. And what we show is that for any number of agents larger than 3, you can find examples in all of these sets. So they are different preference domains. But if we have only 3 agents, then essentially everything collapses. Well, separable additive is equal to the union of the lexicographic preference domains. So that's just how these preferences look like. And our first main result is a categorization of the strong core allocations and the weak core allocations, in fact. Now, again, I just represent the whole result by a Venn diagram, and I need to explain a little bit how to read it. So first of all, the strict core or the strong core for selfish lexicographic preferences is non-empty. And this is for any number of agents and for both unacceptable and unacceptable agents and houses. So this is the most general case. So we have non-emptiness of the strong core. Now, this is one of the main results. Next, what is this set here? This is a strong core. But wait a second, this is a strong core only defined on your selfish lexicographic preferences. This is a strict ranking of the houses. Now, this is the strong core of the classic housing markets where we ignore the externality. Okay, so you just care about houses and you compute the strong core for that. It's a strict relation, so it's a single outcome. Wait. Sorry, I made some statement there. I'm not sure about that. So, and then we show that this is a subset of the weak core, again, for the original housing markets where you ignore the agents who are staying in your house. And then you get the weak core of the separable preferences, of the lexicographic selfish preferences here. So you have this sort of Venn diagram that sorts how your core allocations look like. And we do have examples of allocations, you know, of that these sets can be strict. Okay. So this is the main result. Dominik, how much time do I have?
Maybe a minute and a half.
Okay, not so much. The second result we have is a characterization result. And so I'm a bit quicker here. A rule assigns an allocation to each housing market. Now, a rule that only assigns individual rational allocations, you know, something that's better than your endowment is individually rational. If the allocation is Pareto optimal, your rule is Pareto optimal. And if it never benefits you to lie and misrepresent your preferences, then the rule is strategy proof. Okay. Now, we know that the TTC rule in the original housing markets, I'm not going to introduce it, many people of you know how this works, assigns an allocation to the original housing market. Now, what we do is for the selfish lexicographic domain, we just apply the TTC rule to the selfish preferences. And that's the TTC rule we talk about. So we basically ignore your preferences over the other agents. And then what we do is we extend an original characterization for the original housing markets to our setting. And the theorem we get is that the top trading cycles rule is the only rule on the selfish lexicographic domain that satisfies individual rationality, Pareto optimality, and strategy-proofness. Now, I would like to discuss this just with the remaining minute because this looks familiar to many of you because Ma showed that for the original housing market model, for the Shapley-Scarf housing markets, the TTC, the strict core, which equals the TTC outcome, is characterized by exactly the same properties. So in the original model, we have a characterization of, well, actually, we don't know. Is this a characterization of the TTC rule or is it a characterization of the strict core? Ma presents it as a characterization of the strict core. Now, what this theorem shows is that, in fact, the properties, at least in this setup, characterize the TTC rule. They do not characterize the strict core because the strict core in this context can be multi-valued. So the TTC rule picks a selection from the strict core in our model, in this context, and the properties characterize that selection. So that sort of means the properties don't characterize the core set as such. And so in that sense, I think it's a very nice result because it at least gives an interpretation to what these properties actually characterize. And I think these properties characterize the TTC rule. Okay, so I think that's the second main result I wanted to present to you. We are in the process of polishing the paper. So if you are interested in the paper, just send me an email and I send you a version towards the end of the summer when we have it sort of really polished. And just in case you are interested in the references, they're on the last slide. And I put the handout with the copies of the slides on the COMSOC seminar page. So if you want to check that, you can download the PDF file. So thanks a lot. And that's it.
Thanks. Let's unmute and give a round of applause. And mute again.
Shall I unshare? Or are there
again?
questions? Shall I unshare the slides?
Yeah, you can unshare, yes. So there are a few questions. Feel free to ask more. So the first questions were about potential other applications. So for example, Alan suggests whether or asks whether this is also applicable to exchange student and host family assignment.
Yes, I'm now reading the chat. That's a two-sided market, right? So here we have a so-called one-sided market or no-sided market, if you wish, where we have these objects that we swap, and the houses themselves don't have preferences. Now, exchange students and host families would be a two-sided market, so I would use a different approach. So I can't immediately say, but then of course we know in school choice, the TTC algorithm is sometimes used, so I would have to think a little bit more about that.
And Jerome suggests kidney exchange, where we have pairs of donors and recipients.
In fact, yes, this is another example, and that's a good reminder, because at some point I'm in the European cost action on kidney exchange, and in one of the meetings somebody mentioned that there was a altruistic, that there was a donor recipient pair for the kidney exchange, where even though this pair was compatible, they were actually willing to go into a kidney exchange so that the relatively young organ could go somewhere else and not to the relatively old recipient of that endowment, if you wish. So that was an example of an altruistic preference of an agent in exactly this context. So this is another example that you could use to motivate the example. You might not care only about the organ you receive, but also where your organ is going when you have a donor recipient pair. So indeed, I had that as an example, and I need to, in fact, try to find that anecdotal evidence and add it to the paper. Now, there's another question: is there a rule algorithm, perhaps an extension to TTC, to find an allotment in the core if one exists? Well, yes, I mean, well, for the lexicographic preferences, that's the case. For general separable preferences, it's not so clear, right? Now, Vikram's comment, I appreciate a lot. Say hello to Troy. That's a little doggy. Okay, so these seem to be the questions for the moment. Is the core unique under lexicographic preferences? Is the core unique? No, it's not. So that's the point of the characterization, that the core is not unique. The strict core does not need to be unique. We have an example where it's multivariate. What's altruistic about preference about other individuals? Well, I mentioned, I think with the selfish and altruistic, I had the swapping of teaching bundles in mind. You know, what I teach is sort of the selfish aspect of the swap, and who teaches my original courses, you know, how good a teacher is that person for microeconomics, in the benefit of my students, would be altruistic. That's where that came from. Maybe there's a better terminology. Other regarding and self-regarding, yes, that's actually true. I'm checking that. Although it's not really other regarding, right? Because you don't take into account, so Vikram says other regarding and self-regarding. Both components are still self-regarding, right? If I take the vacation house, it's a selfish interest where I go, and it's a selfish interest how my vacation house looks like when I come back. So I'm not sure. I need to think about a better terminology. William, yes, TTC is group strategy proof. William asked, what about group strategy proofness? Yes, the TTC on the lexicographic domain or domains is group strategy proof. That is correct. Yeah, maybe we should mention that in the context of the theorem. Okay.
Have you thought about any weakenings of the core that might be doable even for separable preferences?
Not yet. So this is a project, it's an ongoing project. So we have been talking about stable sets. And at some point we started getting the results for the core. So we said, okay, let's work it out. And you know, everything taken together with the examples, all the constructed examples, and it's already quite a substantial paper when it's written up. So this is sort of part 2. But I think we don't fall into the trap of calling a paper so-and-so part 1, because we see many examples where we see these articles part 1 and somehow you never find part 2 published, right? But yes, absolutely, that's a good idea.
Cool. Are there any further questions? Yes.
William, what about starting from an allocation and using that to define lower bound on welfare? Yes, we have not thought about that yet. You know, exactly for the same reason that we were just starting to focus on the core and by finishing this. And once we have done that, we are ready for other explorations in the same model. Let me just write this down. That is preference as host. Yes, but then, so Anna says maybe I can use the terminology preference as a host and preference as a guest, but then we tie it to that specific example. So I think a generic name that doesn't, of course, I admit I commit the same crime by having this selfish altruistic thing in mind. But clearly terminology could be better. So I'm asking William on this one because he's very good at these things. So William, please let us have a chat about how to call that sometimes later. I can use some feedback on that.
Right, maybe you will end up being in the same breakout room. I think we should end the session.
Thank you very
now.
much.
Thank you.
Take care.
All right. So let's go into the break, 10 minutes as usual. We will have random breakout rooms where you can talk to other participants or you can get a coffee. Let's see how many.
Dominik, shall I share my screen now or to wait? You are on mute.
Thanks. Yeah, I think you can share so we can marvel at your title slide.
Exactly, something of that sort.
So I'm struggling to come up with password hints every week. So if someone has good ideas, please do tell them. Omer graciously shared a couple of ideas, but I decided they were all too difficult.
Sorry, what did you say, Dominik?
Sorry?
Dominik, can you repeat what you said? You're struggling with what?
I'm struggling to come up with good hints for the passwords every week because they need to be too difficult for a random person and easy for literally everyone who might want to attend.
And apparently you have a low opinion of the people here because you think mine are too hard.
My estimate of the breadth of the audience is very high.
I see.
Right, so right, we have some economists who might not be too much into intricacies of computational complexity, and computer scientists who might not be too much into economics-y type ones. So this kind of restrains things.
Good excuse.
Yeah. All right, Jerome asked whether I can make a list of the hints. I should do that at some point. All right, I think we're all back. Our second speaker is Omer, and he will talk about some spatial problems.
Yes, thank you very much. I'm going to talk about basically what are two different spatial problems, which I've been working on lately. I decided not to go for a talk some of you already heard. So the first paper is with Alexander Karpov and Svetlana Obertsova, and the second one with Zach Fitzsimmons. I'll give slightly shorter shrift to the second one because it will be presented at ICHCAI and at MPref, so it'll get its time under the sun there. We've been talking, I think, a lot lately in the past several years on spatial models, and I think it has a lot to do with distortion, which, while it was introduced without a metric space, without a spatial concept in Prokacha and Rosenstein's 2006 paper, I think since Elliot Ancelevich and John Postel and a few others worked on since 2012, they worked on it, and it became much more popular. I think there's a workshop in a week or two at EC, around EC, by Elliot and Isar and Aris regarding this. So that's distortion, but I'm not going to talk about distortion. It's just one of the reasons that spatial models are so popular lately. And there's, of course, the stream the stream of research that talks about not just conceptual space, ideological space, but physical space. Facility location is, of course, a very long research problem, but in the past decade or so, we've seen research on gerrymandering, which basically takes a geographical space and divides it up, and is, again, a voting problem, yet in a spatial model. So basically, we talk about physical space models or ideological space models. Now, the first topic I'll talk today has to do with ideological space, and the second with physical space or geographic space. But in a sense, and I'll talk about it a bit later, both of the problems I'm presenting can be transformed to the other one. So from the ideological space to the physical space and vice versa, which I think is part of what makes these problems a bit neat. And in a sense, they're not related to neither to distortion or neither to facility location gerrymandering, which I think is slightly different in both of the spaces they deal with. But I think they're pretty neat problem spaces with a lot of open problems. Now I'll begin regarding the first problem, and I'll first start with the problem of where we started talking about it. And it had to do with primaries, and primaries, I'm not going to present the paper. It's a paper by Alan Borden and Isar Chai and Harold Strangway. but it has the idea of locating all the voters in a metric space. In this case, I'm drawing a single dimensional one. And parts of the voters are these parties, and they have a set of candidates. And each party selects from its set of candidates, it selects an outcome. So in this case, the dark green and the turquoise party each turn up a candidate. And then ultimately, the overall metric space, the overall voters choose between these party candidates. Now we began thinking, Alexander Karpov and Svetlana Obertsova and myself, about what can we and analyze once we start making these parties strategic. And of course, one of the natural things to happen is that we should end up in a Nash equilibrium. We actually don't know how the Nash equilibrium should look like, which threw us to a completely different problem from these primaries into trying to understand Hotelling-Downs equilibria in things that aren't plurality and aren't very, very basic. So for those who aren't familiar with it, the Hotelling-Downs model is basically a spatial model in which it has voters are pointing space and candidates are pointing space and preferences are in a sense signal peaked, in the sense that the closest you are in the metric space to me, the higher I rank you. And basically, there's been a lot of analysis of this. It was originally formulated by Hotelling in the 20s for facility locations, and then Downs added in the 50s the idea of talking about it also in the sense of a political or ideological space. Of course, the most common, the right-left single-dimensional space, but many other are bound. Now, most results deal with the one-dimensional space, and that will also be a lot of our research. They almost always use plurality or runoff plurality. There are very few results on K-approval. And the key thing which made a lot of the existing results less relevant for us is that candidates wish to increase their support. It's not a matter of am I winning or am I losing. It's a matter of I'd like to have a larger plurality score, for example. And especially since our motivation came from partisanship, in a lot of cases parties may want to win, but just expanding their support without winning may seem pointless, especially in the ideological for the ideologists among them. So we wanted to have a winner-take-all system. So our variant, the thing I'll be talking about today has to do with the winner-take-all consideration. We're going to talk about plurality, but that's a lot of results do exist. The veto board, others, general scoring rules for 3 and 4 candidates. I'm going to talk about the single dimension as well as a circular space, and I'll explain why when I get to it later on. And one of the things I think is particularly interesting in this analysis, I'm going to talk about probability of equilibrium. And the reason why we're doing this is because in many cases, you look at characterizations of equilibria, and it's not very clear, is this a voting rule, or this a setting where equilibria occurs a lot or doesn't, or it's just very unclear how to take this criteria, this characterization of an equilibrium, and understand whether this problem has a lot of them or not. So the way we chose to approach it, it's definitely arguable, and we argued amongst ourselves, and it's definitely can be open to debate, is to try and at least initially do, say, in this metric space, voters and candidates were uniformly distributed. What would be the probability of equilibrium? And that's a number that we can use to compare different voting systems and different mechanisms, and different spaces even, and say, okay, this is more likely to end up in a more natural way in an equilibrium, and a different state is not. So that's the setting of the problems. Now let's talk a bit about results. So for plurality, most of the results exist. We know that there exists a Nash equilibrium for 3 candidates when voters are uniformly distributed, and the winner will always be one of the more extreme ones, and I'll explain why later on. And for plurality runoff, the only symmetric equilibrium is the median voter. And these are, as I said, existing results. we try to go more general, though for plurality we will generalize some of these results. So let me start talking about the line about veto. And I'll devote a bit more time to veto because it's the easiest to explain, and I prefer not to delve into the technicalities of the more complicated voting rules, which take a lot more time. So first of all, you're seeing before you the result, and I'm using 1 over m and 1 minus 1 over m. This assumes a uniform distribution, but of course it can be for any density function as long as where the probability of the amount of voters is less than 1 over m, that's this edge, and less than 1 minus 1 over m, the other edge. So if you have multiple locations in equilibrium, 3 or more, then it's very clear that there can be no equilibrium if your candidates are located in 3 or more locations. And the reason is simple, because when you're in veto, everyone who's not extreme is never vetoed. So any extreme candidate wants to move to become a non-extreme candidate, and therefore it will never end up being an equilibrium. So we can never have 3 or more locations for candidates. How about 2 locations for candidate? Is that a possible Nash equilibrium? Again, the answer is no. If these 2 are winning, then this one would move here to have at least a 3rd chance of winning. If this guy is winning, then one of them would like to move to the middle and become the winner. So obviously 2 locations also cannot be an equilibrium. So an equilibrium can only happen if all the candidates are in one single location. Now, when they're in a single location, if they're very close to the edge, either here or here, then there's a very clear deviation to move just slightly, towards 1 over m, because more than n divided by m voters will be vetoing these m minus 1 candidates, while this candidate will only be vetoed by very, very few voters, and therefore will end up the winner. So we end up with a very, not very complicated, but very straightforward theorem that in order to have equilibrium for veto on a single dimensional space, you want to be in a single location in these bounds. Now, moving on, I won't go into the proof. For veto runoff, that is multiple candidates being eliminated by veto, that's also the same equilibrium. For Borda, the only equilibrium is where all candidates are in the median voter, and the same is for Borda runoff. And a similar result happens for Condorcet consistent voting rules. And again, it isn't hard in this case to think why, because when we're on the line, the median voter is that's the location of a Condorcet winner. So it's always beneficial. You know that if you move there, you will be the winner, and therefore it ends up being a beneficial location. Now let's move on to a slightly more elaborate thing, and that is a scoring rule in which we don't any scoring rule for 3 candidates, in which basically we parameterize the value that isn't 1 or 0, so the middle value. And we have these 3. It's a theorem that basically characterizes how the equilibrium looks under this scoring rule. And basically we know that the winners will always have an edge position. And basically when alpha is larger than half, they will all be in the same location. So all the candidates will be in the same location. When alpha is smaller than half, they will be in separate locations. There are other characterizations and more, and of course they're included in the paper, but that's like a very high level view of how the equilibrium looks, like. They will always have these properties, and this drawing is attempting to give some form of understanding here, because you see who's giving 1 point to each candidate, who's giving alpha points into to which candidate. And the thing is, where alpha is very, very low, so basically this, you can ignore it. And basically, if a candidate moves to a different candidate, so they're occupying the same point, they're not in the same location, they are in the same location, they're dividing this 1 point, and this guy is taking everything left and will become the winner. So if he moves here, this will become the winner. So this is not a profitable deviation. However, if the alpha is very high, that doesn't really matter, because if you move here, that's fine. You're still getting a lot of points here, and that sort of compensates for that. So now this is a case where I think the probability of equilibrium really makes a difference, because it's great that we're able to have these three sentences, and we have even a more elaborate, which I didn't bother to write on the slides, a more elaborate characterization filled with equations, and that's great, but it doesn't really make you understand when is an equilibrium more likely. And for this, it's very simple to say that for alpha larger than half, the probability is 0, because the probability of all three candidates being in the same location is 0. And again, that's a debatable point. You can try to discretize the space in order to deal with this particular case, problem. The probability is very low. For alpha smaller than half, you can see the probability relies on the alpha, and the smaller alpha is, the higher the probability of ending up just randomly in an equilibrium. And you can see that as alpha grows, the probability of ending up in an equilibrium drops significantly. Now, I should mention, for any elimination rule in this case, the probability is 0. So that's that. Now, moving to the circle, I won't delve in too much into this. There are several results, but I'd like to get to the second results as well. And here we were able to both characterize for 3 candidates and 4 candidates what's going on. In this case, you're seeing the circle used to assume, and the reasoning for the circle, originally it's from facility location. There's been work since the 1980s regarding facility locations problem on the circle. But in the last decade, we've seen both political scientists as well as a variety of researchers in economics and elsewhere talk about Hotelling Downs model in a circle. And it seems to be that the reasoning is this, what's nicknamed the horseshoe idea, that the extreme right and the extreme left are sort of joined, have a lot of shared properties, and therefore the ideological space is not actually a right-left line, but rather a circular thing. And this poses a lot of interesting questions regarding this, how does an equilibrium look like? And I'll just point to the results here. And again, the characterizations are pretty intricate, and I will just show you a long list of equations. But basically, for alpha larger than half, the probability of equilibrium is 0. They have to be in the same location. For alpha smaller than half, the probability is 1/6. And notice that while on the line, the probability had to do with alpha, when alpha is smaller than half, it doesn't have to do with alpha. It is independent of the actual alpha. It's always a 1/6. And when alpha is equal to half, the probability is 1. And the reason for that is you just put any locations for candidates, you will end up in an equilibrium. So it's any location will end up in equilibrium when alpha equals half. And the elimination rule, the probability is still 0. And when you talk about 4 candidates, for plurality, the probability is still 0. Plurality with runoff, somewhat surprisingly, is actually a quarter. It's, I think, the only case we've found that that there's a high probability of ending up with a runoff winner rather than the regular voting rule is this case. And for Borda, and this is true for any number of candidates, not just 4, for Borda, the probability is 1. Any location, you will always get, every candidate will get the same score. And for veto, similarly, because there's no edge. You're always finding someone to eliminate. So that's this about the Hotelling Downs equilibria, and I'll talk a bit more about it towards the end when I'll sort of wrap up everything I've shown. And now I'm going to move to a completely different problem, which is in geographical space. No longer ideological space. We're not going to talk about where candidates and voters are located, completely different. But now I'm going to talk about voting locations. And this is, as I said, I work with Zach Fitzsimmons. We presented at IJCAI and at MPref, which is sooner, I think. So what's the problem we're talking about here? This is geographical space. Voters are located on it. They're having a great time. And each of them has a certain distance they are willing to go in order to vote. So if they have a voting location within a particular radius, they're willing to go there. If they don't, they won't vote. And there's a set of possible voting locations. You can think of, I don't know, public buildings, schools, whatever. And you need to select at least K voting places, so people will go and vote. Now, the thing is, can you make a particular candidate win? Now, you can say, well, this is a very weird manipulation, control problem. It probably never happens. This is complete irrelevance. Why are you showing us these made-up problems? And the reason for this is this completely not a made-up problem. This is from last month, removing polling places for locations of minorities. This was in Texas. This one in the 2018 election regarding removal of voting sites, particularly subset of voters, hurting particularly them. And this is an analysis from Mother Jones regarding the 2018 election. And they found that 1,600 locations have been removed, and they do have a particular location. There's a particular partisan location. They do influence. They're removed more in places where one party is stronger than the other, so it hurts a particular party. It's not a uniformly, it doesn't have a uniform effect on the outcome. So this is clearly something that there are people who are doing this control problem and trying to do this, and we wanted to understand how hard is this problem, can we understand it more fully, and indeed towards the end, how can we actually do something to sort of counter it. And the first result, and this is in a sense the only result, which is not the only, but the main result, which is let's say a positive one. For two parties on a line, you can find using a dynamic programming, and I won't go into the details of it. You can find a dynamic program that results in a candidate winning, in a particular candidate winning. Anything else, almost, apart from several additional constraints, will not work. So, for example, even on the plane with two parties, even in which each voter is equivalent to any other one because they have the same radius, this is NP complete to manipulate. And I think I'm close to running out of time, so I won't explain this cute little gadget here, but it's a cute gadget. If you can see the paper, I think it's a cute gadget. Voters on the line are also, if you move beyond two candidates to three candidates, that becomes NP complete and in fact inapproximable by a fixed amount. So basically it works for two candidates on the line. For anything else, it's either for two candidates on the plane, it's already, even greedy algorithms don't work. We haven't proved it's inapproximable, but the obvious algorithms don't work. And for three candidates or more, it's inapproximable. So, so this seems like, okay, where do we go on from here? So there are several interesting results. I think the paper got, if you had some constraints on the geographical space, they'll help you solve it. But there's one particular neat result which I'd like to mention, and that is that attempting to change the winner by changing the distance of the voter's radius is NP. And this brings up a possible application, which I think is a great future avenue of research, and that is about buses. Because buses, in a sense, if you're busing voters, you are, in a sense, you're enlarging their radius. Because instead of, say, walking to a voting place, you're driving them so they can go further, or they don't need to drive themselves. So they're willing to expend their time, is basically they're willing to expand the radius if you're, in a sense, shortening their time. So in geographic space, can one design, say, a bus route that will ameliorate the effects of taking voting places and removing them? So I think that's a pretty interesting future direction. So I think I'm running out of time. I'll just note two additional things. First of all, notice that the two models which I've discussed, both the hoteling down and the voting places location, have an applicability in the other domains. So the hoteling down equilibria I discussed were ideological. We have candidates locations and voter locations, and this obviously has an equivalent when you're talking about facility location. Where do you place items and how do you choose where to select locations? And this also has to do, and the opposite direction also works, because the voting places locations, the geographical space, where they have this radius, in a sense can be adapted to talk about a willingness to pragmatize. So imagine in the ideological space, this radius is how much am I willing to move beyond where I am ideologically to vote for someone. So again, this requires you can't just take the results and move them. but it opens up a very similar problem, and there has been a somewhat similar paper which I recently discovered by Svetlana Obraztsova and Amos Fiat and Michal Feldman about this. But I think this radius of ideological space of where am I willing to move has a lot of interesting future directions that can take part of our results and adapt them to that domain. So as I said, there are a lot of future directions here. I think more strategy is true for both. And I think particularly for the Otelling's down thing, primaries and votings, which are our incentive to begin talking about this, can be used in this model in a very interesting and not trivial way. And for voting locations, as I said, bus routes, I think optimizing proportionality is something that we haven't talked about at all. We've tried to optimize for particular candidates, and optimizing for proportionality might be a very interesting thing, and seeing if that's actually easier to do. And the final thing is, instead of this radius being a binary thing, either I'm willing to vote here or not, it could be a probability aspect. So the closer you are, the more willing I am to vote in this location, and the further away from the voting location is, the less willing I am to vote there. So I think these are several directions which I think are pretty neat. That's it. Thanks for listening.
Thank you.
Okay, I haven't looked in the chat, but let me...
Yeah, several long questions. So let me read Paolo's question, who's asking, you seem to be treating parties as non-overlapping intervals, so they always have fine-grained enough candidates, but why? Typically, there are 3 or 4 acceptable candidate nominees per parties at quite some distance from each other. For example, look at some people in the British Conservative Party. This is going to make quite a difference in terms of equilibrium existence.
Right. So I agree that when we talk about parties, that is definitely true. They do overlap, but the thing is, ultimately, each party presents a single candidate. And inside the Conservative Party, May, Johnson, Rees-Mogg, say, occupy locations, and the party decided between them. And then ultimately, they presented one outcome to the voters. So the voters saw, the general election saw only Johnson. The fact that Rees-Mogg was running or Johnson was running is great, but ultimately they presented one. So, but I think you're right in a more general sense that a party occupies in people's mind may be a spectrum. So when you think of, am I going to vote for this conservative candidate or this Labour candidate or this Lib Dem candidate, then you're not thinking about a point in space, but a range. And I think that's a very interesting modification. But what we began by trying to see, okay, let's see that we're understanding the basic parts for the primary, just giving a location for a candidate. Then we realized we actually have no idea what the equilibria is like. And that's why we tried just examining the equilibria, because we realized this is not a solved problem. We're both, when we started working on this, sure that the equilibrium issue of single location is solved, and we realized it wasn't. And then we began this work, which took us to a completely different place. I agree that talking about ranges is an interesting thing and hasn't been done as far as I know. And
sorry, can I add to that? Sorry, I don't. So my point was that if you have finitely many choices per party, you end up not having equilibria if parties overlap. While in your framework, there seems to be always an equilibrium. Okay.
So I'm not sure. So for when overlapping is beneficial, I'm not sure why that will not be an equilibrium. I can definitely see cases where, again, it's depends on how fine-grained it is. For example, if it's fine-grained enough and we have if a small enough party number, like say Britain or Canada or the US or all that, I think you end up with the fact that even if you discretize the space into enough like subsets, you will still end up with these equilibria, I think. I need to think about it some more. I don't want to just throw it out, but my initial, the obvious places to manipulate seem to exist on the face of it. So I don't want to say something too stupid, but that's my intuition. Okay.
So Nisarg asks a related question, though I think you've answered it, because you say there's no research about parties that present themselves as intervals, but he suggests having a cost. It's more costly if you are a broader interval but your benefit is
I
that you're
need
closer
to
to more voters.
Regarding Bill Zwickert's question on the line and the circle, I'm not sure. So I'm not sure it plays a huge. The fact that it's compact plays us in a role in a sense that I think it's more the roundness rather than compactness. The fact that you can never be too distant from me in a sense. So, and if you try to become too distant from me, you'll be close enough to me. So in a sense, for example, you're trying to separating, say in border scores, you'll end up with, if you try to separate these voters, they'll end up too close and they'll have the same score. So I don't know if it's the compact, I feel it's more the fact that it's a closed shape that makes it. Which is actually its compactness in a way, but so I guess the answer is yes to that when I speak out loud, when I say it out loud. Yeah, so I think I answered that question by Nisarg. That's anyone with a difference. So in a sense, I think veto is looking at the difference, right? I mean, at least intuitively to me, a veto voting system, Judy, is looking at your most hated candidate or your furthest away candidate, and that's the candidate you wish to eliminate. So in a sense, the veto voting rule is sort of what I really care about is the furthest away candidate for me. But you're right that it may, if a utility function that looks at who I hated, like if you say like there's the opposite of single peak, a single dip, or I don't know how to determinize the type of vote of preference distribution. But like what I really care about is who I hate, and the further I am from who I hate, the more I like them. So I guess that's an interesting avenue. I'm not aware of any research that does that though. Oh, regarding location in parties, Judy, you mean a pay? Oh, sorry, Edith was referring to Judy. So regarding
one comes in two parts. So there's a question for you, and then I noticed Judy's comment and started typing a response to that, and that came out as one answer.
So yeah, I agree. There's definitely strategic candidacy, and I think, you know, I gave like, I think 5 talks in the last year on primaries, which is why I chose not to bore you again with another talk of primaries. But I think this whole strategic location of what candidates choose to do in this multi-stage thing is definitely a huge open problem. They may realize their presence in the it's a very intricate problem, and I think a very neat one. I'm very excited to explore it, but again, we realize at some point we want to explore it, but a much more basic problem isn't explored, so we're taking it step by step. But yes, there's lots of, it's huge problem space, and I think I find it very interesting, of course, but yeah. I'm not aware of any result on that so far. That's it, I think.
I think so. Any more questions? Yes. Omer, do you see the
what?
question on buses? There's a new bus question.
I didn't see it. Where is it? Oh, here, yes. Right, I think, Jack, that's an interesting point. So I admit that we thought about buses in the physical space, that they will allow us to shorten, to extend the radiuses. But you can imagine in the ideological space, an equivalent is sort of a candidate that can pull, say, enough distant candidates, sort of like in several locations at once, is able to extend the appeal of himself. I need to think about it some more. I admit I haven't thought about it in the ideological space equivalent. But I guess you're right that it may have some form of a thing that is, maybe a particular candidate can have the power to pull to pull distant voters closer, in a sense.
All right, thanks for all the questions. Our next meeting will be in approximately 2 weeks, Thursday the 23rd of July. Now this July we were planning to have a great COMSOC workshop in Israel, but that's not happening now. But instead, let's have a special session with 2 speakers from Israel, and that will be Omer and Gil Kalai. And that will be in about 2 weeks on Thursday. In fact, we will switch to Thursday as our standard day from then on, and meet only a couple times in July and August, and then restart properly in September. Ulle just announced that there will be a rump session in September, and then everyone will be welcome to volunteer for a 5-minute talk. So with that, thanks all for coming, and see you in about 2 weeks.
And thank you, Dominik.
Thank you.
All right.
Thanks, Dominik.
Thank you.
Okay.
Bye.
Bye.